All right, so today we'll be talking about Bayesian classification, which is our third classification model we're going to be talking about. Just for some context, Bayesian classification is actually mostly used when dealing with text data. And because we haven't dealt with text data yet, I will go into a little bit of NLP detail before we get into NLP next phase. So that's natural language processing. Your project should not be an NLP project. We'll save that for the next phase. I anticipate quite a few of you will be doing NLP projects, but the way that the algorithm works is exactly the same. So just so you know, in case you see like words and are confused by like, how do we deal with that? I'll be going into a tiny bit of detail just for the sake of explaining the problem that we're trying to figure out in this notebook. But yeah, Bayesian classification brings back our Bayes theorem that we talked about. I believe it's topic 17 from the last phase. So naive Bayes classifier is great because they are simple and very efficient. It's probabilistic. So here there is actually no cost function. All we're doing is computing a probability. So this is, I think, the only model that we're going to be talking about in this phase that doesn't really have like a gradient descent cost function, because we're really just computing the conditional probability, of which I'll break down in a little bit. So probabilistic model based on Bayes theorem, and naive, it's actually called the naive Bayes classifier, comes from the assumption that features in the data set are mutually independent. Independent in different contexts can mean different things, but in this case, you're assuming that each of your features, so each of the columns in your X data, are independent. By independent meaning that one doesn't affect the other. So for example, price of a house, square footage doesn't affect the number of floors in your house, which is not completely true. It is slightly related and not fully independent, but in practice, this independence assumption is often violated, but naive Bayes classifiers still tend to perform very well under this unrealistic assumption. So especially for smaller sample sizes and for text data, naive Bayes classifiers outperform the more powerful alternatives. Questions about this so far? I know this is just an intro, but any questions? All right, so these are the examples that we're going to be working with our small example in how I talk about, this these probability equations. So here, imagine we have two classes of text data. So first we have some sports data and some politics data. So for example, these are just some sports lines, like the match was close, coaches agreed on a strategy, played in a sold-out stadium. Now we have some phrases about politics. World leaders met last week, the election was close, officials agreed on a compromise. So we're going to build a model to be able to predict other statements that aren't these. And our test statement that we're going to use that is a little bit ambiguous. World leaders agreed to fund the stadium. So we're going to see that based on this model, based on this model, is this test statement going to be classified as sports or politics? And so we'll see. So as a quick review of Bayes theorem, this is what Bayes theorem looks like. The probability of A given B is equal to the opposite conditional probability multiplied by probability of A over probability of B. Using English words, I say English with quotes because it doesn't really help. What we're trying to compute is the posterior probability, the probability after the fact, using the likelihood of something occurring with a prior probability and the predictor's prior probability. And this is just the function of the law of total probability, which I think it might be missing a part, but no, I think that's right. All right, so in our context, let's say we have our two labels, L, L1 and L2. This is how we interpret this equation. So the probability of your label given your features, so features in this case will be our words, the probability of something of this test statement being politics or sports given the phrase will be equal to the probability of the features, the probability of the words occurring given that it's a certain label, multiplied by the probability of the label occurring, divided by the probability of the features. So for each class, we can compute this probability. We can compute the probability of, all right, for this test set, for this test phrase, what is the probability of it being politics, given the features? And what is the probability of being sports, given the features? So we're going to compute these probabilities. One piece of the puzzle that makes it a little simpler is because we're going to be looking at both L1 and L2. Let's say L1 is sports, L2 is politics. We can actually rearrange this to look like this. So what we're doing here, if you actually take a look, imagine each of these has an L1 or an L2. What remains constant is this denominator here. The probability of your features for any phrase will be the same because here it doesn't take into account which label it has. So you can sort of rearrange this and equate both sides of the L1 and L2 equation to create this. So after we've rearranged it to see both L1 and L2, you see here that we don't need to compute the probability of the features themselves, which is one less thing to compute, which is great. Questions about this so far? Cool. So
L1?
Yeah.
L1 and L2 are our target variables?
That's right. L1 and L2 are our target variables.
Okay.
I know shouldn't use L1 and L2 because that's like our regularization parameters usually, but that's what it is in this example. So in the context of our problem, what is the probability that given this document or given this phrase of world leaders agreed to fund the stadium, given that phrase, what is the probability that it is politics? Oops. Will be equivalent to the probability that given it is politics, what is the probability of the document occurring, multiplied by the probability of politics, and again, divided by probability of document, but we don't have to compute that because we can equate L1 and L2 both. We can compute the same thing for both politics and sports, and you won't need to compute the probability of the document itself. So just to break it down, let's start with, I think, the easier part. How should we calculate probability of politics? So literally, it's just a distribution of the probability of each type of article. And so because in our very small example here, we have 3 examples of each sports and politics, it's literally the number of politics documents over the number of all the documents. That makes sense? So for this, literally, number of politics documents is 3, number of all documents is 6. Probability of just politics without any conditional probability is half. So here you can see I did the same thing for both politics and sports. Here we're taking just the length of those lists. And actually, let me move this down so we can see it more clearly. There we go. This is our training data pretty much. Length of politics divided by the length of both politics and sports. And literally, it's just a proportion of all your training data that is either politics or sports. Cool. All right. So I think that one is more straightforward. Next, how should we calculate the probability of a document given that it is politics? So to do that, first we got to break the phrases down into individual words. So here's our test statement. Let's just take a look at this again. So the probability of a document given that it's politics has to be broken down into its words. So here you can see the probability of a phrase given politics is going to be the product of each word occurring given that it's politics. So this symbol is the mathematical symbol for multiplying everything together. So if you remember like that E looking symbol, that sigma for summing everything together, this is for multiplying everything together. So for each word, we're actually going to find the probability of the word given that it belongs to politics, and then multiply this probability for every word together to find the probability of the phrase given that as politics. And from that, how do we get each word's probability? The probability of each word given that it is politics is just the number of words in your politics documents over the total number of words in your politics document. Let me say that again. The number of times a word occurs, each word occurs in politics documents over the number of times, over the number of total words in politics documents. And I stumbled over my words a little bit, but did that make sense? All right. So you run into a little issue here. What if you see a word in your test statement that your model hasn't encountered before? So maybe, let's say, I wonder if there's like one word here that hasn't been in our test set. Let's see. World leaders agreed to fund the stadium. So fund is a word that didn't occur in either of these trained data sets, right? So because of that, when you find the probability of the word fund, given that it's politics, you end up with a numerator of 0 here. And once you have this as a 0, because you're multiplying everything together, if you have that 0 there, no matter what your other words probabilities are, the product sum becomes 0. So that's not good, right? Because you still want to consider your other words. You don't want one word that doesn't occur in your data set to throw your entire model off. Because of that, we have this concept known as Laplace smoothing. So Laplace smoothing really just adds a constant such that your probability doesn't go to 0 at all. So typically alpha here, so this is the equation with Laplace smoothing. You can see it's pretty much the same equation here for each word, but you're just adding some constant. And here you're adding your constant in your denominator here. So the constant here is typically 1. This is actually something that you can adjust as one of the hyperparameters in your naive Bayes model. Typically, a higher alpha leads to, will help you, kind of works like a regularization term. And here at the denominator, you're adding alpha times d, and d is just the total number of words that you have. Cool. So next, after you have this, you can pretty much compute your probability for the phrase occurring, given that it has that label. All right, so again, for the probability of the document, it doesn't change whether you're looking at either class, so you don't have to compute this value at all. So again, why is this naive? Because it makes the assumption that the features are independent, and it's naive because it's almost never true. This is a Towards Data Science blog post that explains that in more detail. So let's apply our equations really quick. So first of all, to just set up, this first column has all the words in our test data, in our trained data, sorry. These are all the words that occur in our training data. And this is really just counting how many times each word occurs in each class. So you can see here the word the appears twice in both politics and sports. Another example, world only appears once in politics, 0 times in sports. So you can sort of imagine, just conceptually, if a phrase has the word world in it, it will more likely be classified as a politics post rather than a sports post. Conceptually, this is where that comes from. So plugging in our equations, we're going to first find the probability of each word occurring in politics. And these are the words from our test sentence. So based on that, you can see here, let me zoom in so you can all see a little better. So here, this equation basically breaking down, this 1 here is the number of times the word world occurs in politics posts. This 15 is the total number of words that exists. The 1 here is your, the 1 here is your alpha for your Laplace smoothing. And the 30 should be the total, the total number of words that occur, I believe, the total number of words multiplied by your Laplace number, which is 1. So I believe there's 30 words that occur in 1. And basically you end up with a fraction of 2/45. And your overall probability for this test sentence having the label politics or sports is just the product of each of these individual probabilities. Does that make sense? All right, we can like stare at this for a little bit. But what these things are being added at the end of both the numerator and denominator are the Laplace smoothing numbers. All right, so let's translate this into Python. I don't do this regularly, but this is one of the few examples where I do think it is kind of helpful to hard code. But definitely you don't have to do this if you feel like it'll take up a lot of time, I do have an example implementing it in with the scikit-learn module. But first, let's just use these initial imports. What I'm doing here is I'm creating a vocab maker that creates basically the set of words that appear in each category. So here you can see, for example, vocab of sports is just a set of all the words that appear in sports, and same for politics. And also I have one version that is the total. So here I'm also setting the counts, and these are going to be used for our Laplacian smoothing. Next, this basically does the same thing that we did before, the number of words per category. This is just I won't go into detail about what this does, but we'll take a look at the output. So running this and running this. For our test, for our test data, these are the word counts for the number of words in the category. And then same for politics here. Basically, how often does each word appear in the category? So with that done, we can find the likelihood. Same function, same formula being applied here, likelihood. And when you're done, you can see that, oops, what did I not run? Total sports count. Sorry, guys. Total sports count is here. Here you go. I did not run this cell. So with this, you see that the probability of it being in sports is 1.53 to the negative power of 10. Probability of politics is 3.06 to the power of negative 10. And what we're checking to see is which one is more likely. And it is more likely that it is politics, because the number for politics is greater than the number for sports. So this just goes to show that there is no cost function that we're really optimizing for in this equation. It's really just plugging into Bayes' theorem. Questions about this so far? I feel like I tripped over a lot of my words, so yeah.
Maybe you already explained this, I'm not sure. What would be like a practical example of using this, I guess, in like a job situation? I mean,
Yeah.
with this, like, do they use this if you're working for like a newspaper, like a journalist website? Do they use this type of thing to like classify articles, or?
Yeah, so actually in more recent years, there have been a lot of text classification models that are built to, one, look out for, I know one of the more like socially relevant ones are like how politically leaning something is. So you can actually build a classifier on, like, I believe they are actually trained on, you know, the different news sources and what they are known to lean towards. And you can actually build a model that like classifies any text basically if they lean more left or right.
Oh, that's cool.
Yeah, it's pretty interesting. I actually had one of my bootcamp classmates actually created like a Google Chrome extension. And that was to detect whether an article was a troll article or not. And they basically trained it on like the Onion posts versus just like regular news articles. So for text classification, I feel like there's a lot of, you have to get creative of like how you would use like a classification model. I know for like some businesses that collect reviews, you can actually classify your reviews based on like different categories and things like that. So you can maybe as a business figure out what to focus on. So yeah, quite a few applications of text classification.
There's a Reply All podcast episode that talks about the hedonometer, which I just put the link to, and it just classifies like how happy the world is based on Twitter data. And I think it just breaks up like the text classification for specific words and like time relevant data. So it's pretty interesting to look at because it's made by a few data scientists.
That's awesome. Yeah, we're actually going to be talking about that more in depth when we get into natural language processing. Like sentiment analysis is a huge part of natural language processing, and it's very, very relevant now because how do you derive, context from just like straight up words? It's very, very cool. And yeah, we'll be talking about that next phase, which is very exciting. I love NLP. Any other questions? All right, so before I get into, oh, did I hear? I feel like
I just remembered in the lab they did the log probability, and I can't remember why they talked about using that rather than just the straight up probability.
Off the top of my head, I can't remember either. So I'll take a look at it and then I'll post it in the Slack channel.
I can also be less lazy and just go back and look.
That is also true. I'll probably just Google it and then send whatever resource I find. Okay. All right. Have that written down. So yeah, before I get into like the scikit-learn implementation, we'll talk about like just some pros and cons and like to summarize naive Bayes. So Pro is very, very efficient to predict your classes, and it performs fairly well in multi-class predictions because it's really just based on, the probability of something occurring. It takes into account like how often each feature appears in each class. So very, very efficient. There's no cost function to optimize. Out of all the models, it's one of the fastest ones to run. So if that is something you want to consider, like how fast your model takes to train, naive Bayes is usually one that performs well on that front. So when the assumption of independence holds, so typically like if you can say that your different features are more independent of each other, your naive Bayes classifier will require less training data and can perform better than other models like logistic regression. I think some of you who have tried logistic regression on that mini project, it doesn't perform very well, but naive Bayes, maybe try that out and see. So naive Bayes is also known as a bad estimator. So therefore, the probability outputs from predict prob A are not to be taken too seriously. By that, what I mean is you take a look at these probabilities. These are all to the power of -10. Like, what can you really say about these probabilities? We're really just comparing which one edges out the other more. I think that might have something to do with the log prob, but I have to like read into it and double check. And then we're assuming independent predictors. So that, again, the con, in real life, it's almost impossible that we get a set of completely independent predictors, but amazingly, this model still performs fairly well overall. Questions about any of that? All right, so let's just do a little bit of implementation with scikit-learn. There's a pretty cool thing that I wanted to show you all, but we won't really do it until next phase, but I think it's pretty neat. So what I'm going to do is I'm going to import data sets like we did with the iris data set. Scikit-learn has built-in data sets. Here we can actually fetch news articles from specific topics. So you can see here the way that this works, you just tell it what kind of topics you want to get from that built-in data set. So from that, what we're doing is we're first going to fetch some data. And here we're going to do some baseball articles and some politics articles. And these are actually two different subsets in that database. So it will be, they will be unique from each other. And then I just set my data frame up. I did not run this cell. There we go. So let's just take a quick look at what our data frame looks like. So let's look at df train. df train right now has this pretty messy looking text data and has your target here. So 0 and 1, just to take a look at what 0 versus 1 are. 1 is going to be baseball, 2 is going to be about, 0 is going to be about baseball, 1 is going to be about politics. So just really quick, we have about 1,000 articles in our training set. And let's take a look at how balanced our classes are. So fairly balanced, maybe about like 100 off, but I think this is pretty balanced. And again, to just take a look at what each article looks like currently, very, very messy. Like, how do we even make sense of this? So the thing I wanted to show you all is vectorizing text. So vectorizing text, we'll talk more about this when we get to NLP, but vectorizing text, scikit-learn has just some really, really great built-in things to make vectorizing text easier. And vectorizing is basically the process of taking text and turning it into some representation by numbers. So as we did before, we represented numbers based on like their word counts here. This count vector does exactly that. So Vectorizer, all you have to do is instantiate the CountVectorizer, which is very nice. And you can fit transform your chain set and transform your test set. And we can take a look and see what that looks like. Super awesome, I think this is. So just automatically with that CountVectorizer, it turns every unique string of text usually separated by a space, into its own thing. So typically, and we'll get into this more, you'll usually like filter out these random, like these are not actually words, but they're probably symbols that just occurred in the text document. Usually we filter that out. We're not going to do that for now just because we're not going to get into that. But this is what it looks like. It turns each article into a representation, into like a vector of numbers. So you can see here, this is actually a almost 20,000. Yeah, it's a data set of about almost 20,000 columns. So here again, we're just setting our Y train and Y test. Just in the same way as we did KNN and logistic regression and linear regression, you instantiate your model first, fit it to your train set, and you can make predictions on your test set. So just super quick, you can see that runs pretty fast for like something with 20,000 columns. And let's just take a look and see how it predicted. So this is on our train set. Pretty awesome. On our train set, it actually had a perfect classification. Nothing was misclassified. Let's take a look at the metrics. I expect all ones. And for our test set, out of about 4,000, 3,000, 4,000, you only misclassified 20 sports ones as politics and 10 politics ones as sports. So that, I think, ratio-wise is pretty good. We can take a look at our metrics just like that, all around like a 95 accuracy, precision recall, all around 95. So that's just very simple implementation of naive Bayes. And again, something to tune, which I don't have it pulled up currently, but naive Bayes. Something to tune would be how much you do your smoothing. So it seems like the default here is just like a very, very small decimal, but you can change your smoothing to be any number. Cool.
I have a question, kind of. So even with words like the, or like something that should probably occur in like both of them, it like somehow knows that it would be more likely to occur in one or the other, and then it has that, like, I don't know, it just seems crazy to have like an accuracy that high, I guess. Yeah. With like certain words, I don't know.
So if like the word the is appearing on both sides, but about the equal amount on both sides, the probability for that specific word won't really weight it to one or the other. One pretty cool thing, let me just see if I can get it out of here. You can sort of get your parameters from here. So let me just see if I can extract it from this. What's this model called? Called it model.getParams. Oops. So, oops, not params. I think it is there is a way that you can get like the weight of each word. And I forget which one it is. Maybe it's the predict prob A, or I'll look for it and I'll put it in I will put it in the class channel. But there's a way to get each basically how much each word is pushing the test point towards each class. So yeah,
so I'll put that every time it encountered in the test data the word the, it would, if it was like kind of 50-50 in the training data, about 50% of the time it would classify it as one versus the other, or no?
More so, I sort of like to think of it as like you're starting with your test data point, you sort of start in between both classes and you don't really know like which one it is yet. And then as it encounters each word, it has some sort of like coefficient that pushes it either closer to sports or closer to politics. Yeah, I like to think of it that way. I have to look for which method exactly that is. But yeah, I'll post it in the channel. I do have it somewhere for sure. But also to your point with like words like the, a, like in, I don't know. So all of those words, when we get to NLP, we'll actually know that these are stop words, and those are actually words that we would clean out of our data set, so that you don't need to like
Okay,
consider those like contextless words.
got it. Okay.
Yeah, but oh,
Is there a way to use this for prediction, like our first example?
absolutely. So what you would do, so let's see, I don't know if I can do this on the spot, but let's see if I can do, so let's say I have, let's see, you would have to first transform your prediction, right? So let's say, I don't know if I can do this on the spot, but we have time, so let's try. So let's call this test 1, and let's say we don't know if this is sports or politics. Let me change this to be double quotes so it will work better. There we go. So let's say I have this test. Usually what we have to do is we have to do a, we have to transform it with the same CountVectorizer. So for example, let's see, how do I do this? So we'll do Vectorizer dot transform X test. Nope, not X test, test 1. Let me see if that works. Over raw text document. Okay, I guess I can't do this now, but basically what you would do is you could actually create a pipeline that will take any text and turn it into the same columns that were in your train set, and then you can feed that as an array into your prediction function. Again, with the NLP, it's very different for words. You can use this exact model for any data set, pretty much. You can do this on that credit card data set that I sent out for your mini project, so you can implement it in exactly the same way. But when we get to NLP, I do have examples of this in some of my other notebooks where I walk through how you can make new predictions.
Okay, thanks.
Is that what the
Can't do this
purpose?
currently.
Is that what the purpose of the make pipeline function is?
Kind of, yeah. So typically what I like to do for my projects, especially when I want to like create like a prediction function that I know some of you did for your linear regression project, I like to have a pipeline that will be able to take in your data in like its raw form. So in this case, your raw form data will be this text, although here it says it expected raw text documents where this was a string, but whatever. Yeah, I usually like to write a pipeline that will turn my data from the raw form to the form that the model can read it. And so, yeah, that would be a use case of like making your pipeline, making a data cleaning pipeline. Typically, it's called like a data pre-processing pipeline. And that typically will also include like your scalar objects if you scaled your data, your get dummies if you're doing that. So yeah, I'll have an example of this when we talk about NLP. So let's not look at this for now. Any other questions? Cool. Well, naive Bayes, again, a simpler model, I would say, like typically when you're working on projects, it's just a good one to throw in there because it runs pretty quickly. Whether you end up using it or not, you do have to compare its performance with the other models that you are using. But yeah, hope you are all working on your mini projects. It's really going to be beneficial for your final project just because the final project, one, is going to be individual. So you want to make sure you get that practice in. And also your mini project has the exact same format as the final project. So we can talk about it at one-on-ones. I can go through like just make sure that the structure of your modeling process makes sense. So make use of that. But cool, that's all I had to share for today. Any questions to close out?
You mentioned that you can use this for the mini project too. Isn't that numerical data? This is dealing more with text. Can you talk about
Absolutely. Yeah, let me actually like import over the numerical data. Or you know what, let me just see, I have another data set on my computer that I can just throw in here really quick. Let's see. Sorry, give me a second to get all of this information. Okay, so I have we're just going to use the iris data set real quick. Let me just copy and paste some code here. So we have our iris data set, and I need to import data sets real quick. All right, so now we have our X iris and Y iris. Let's do all right. I won't do train tests for this, but you can really just implement it in exactly the same way. So I have that model as naive Bayes here. I'm gonna do, I can just call it model 2 for now, and then I'll just do model2.fit on my X iris and my Y iris. And in exactly the same way, you can do predictions. So model2.predict, you could do that on, because I didn't do the chain test split. This is bad form. You always want to do chain text split, but you can make your predictions just like this. And you can also get your what am I trying to say? Your scores. So let's see if I have this imported. But for example, your accuracy score, predictions. You can do your Y test. No, actually, this is going to be Y iris versus your predictions to just see what your accuracy score is. There we go. So we have a 96% accuracy. Of course, you want to do it with the train test split, but it works the same way with your numerical data as well. Cool. Any other questions? All right. Well, again, make sure that you that you're working on your mini projects. I don't think I have anything else to add. And if Stephen wants to plug our happy hour. Oh, yes.
Super quickly. So the mini projects are supposed to be like you do it individually, but you discuss it with your group, basically, as you go along. Okay.
Yeah, I don't need you to be like running each model over and over again, but I do want you to have the practice of just implementing models and just figuring out your classification metrics, like your evaluation metrics. And the discussion just comes about in like, if any of you are doing different data cleaning, does it affect the model's performance? Or are you testing different model hyperparameters? That's also something that you can talk about. And maybe even before you run a model, maybe say like, all right, maybe you run this parameter, you run this, you run this, just compare your results.
Okay, gotcha.
Yeah. And Stephen, do you want to plug happy hour?
Sure. So there was good response for happy hour, so I was planning on doing it tomorrow evening. And if you want to have fun and get to know your classmates, you should come. And maybe we'll play some board games or we'll do some whiteboard drawing, pretty crazy stuff. If you're planning on coming, maybe just reply in that message I recently sent today. And also I was thinking 6 p.m. Eastern. If you would prefer maybe 7 p.m. Eastern or another time, just reply in there and we can find out what works best for everyone. That is all. Hope to see you there.
You are also welcome to use this Zoom link because this Zoom link is technically always open. So feel free to use this Zoom link if you want to just hang out.
Okay.
Yeah. So technically for like any of your like group projects or like mini projects, if you ever wanted to talk, you can pretty much use this Zoom link if someone isn't already using it.
Or for drinking.
Yeah, you can do that as well. So yeah, again, really want to emphasize that it's a really, really good opportunity and has a lot of long-term benefits of just getting to know your classmates. Like I still am in contact with my bootcamp classmates from like 2 years ago now. We talk like literally every week. So it's just good to know like, and because as you get into your jobs, everyone starts to specialize in something different. And so it's always a good opportunity to like learn from each other. Like I have friends who are in like search optimization, in customer churn, and I just learn a lot of different things based on what they are doing. So definitely good to form this more professional data science network. So hopefully you all attend that.
Yeah, I didn't sell it too well, but it's fun.
Yeah, it's gonna be fun, I know. All right, well, I will leave you all today then. I will see you all at your one-on-ones or at tomorrow's study where we'll talk about decision trees, one of my favorite algorithms. So as usual, any questions, feel free to just let me know. All right, have a good rest of your day, everybody. Bye.